In this video, we're going to look at two-sample testing. In this first example, we'll be comparing two means. In the next example, we're going to look at comparing two proportions. So let's read through this first one. At age 9, the average weight and average height for both boys and girls are exactly the same. A random sample of 9-year-olds yielded these results, and we see the results of the samples below. Based on the sample results, can we conclude that the height of both boys and girls, there are our two samples, are the same, which looks like an equal sign for our hypothesis, at the 0.05 significance level. So this is our alpha. Alpha equals 0.05. So what we have here is not just a single mean that we're comparing to a number, but we have a mean for the boys and a mean for the girls that we're comparing to each other. Let's go ahead and put our hypotheses together. We're just going to step right through that same 5-step hypothesis testing procedure. The first step is to set up our hypotheses. The null hypothesis, well, I'm using an equal sign, but my claim is that they're equal. My claim is that they're the same. We're comparing these means. So the mean for the boys is equal to or the same as the mean height for the girls. The other thing we could do here is to number these. So we could say that the boys is sample number 1 and the girls sample number 2. And that would mean that our hypotheses would be mu sub 1 equals mu sub 2. The only reason I do this is because your book, so that it's generic and it fits all of the problems, will use this subscript 1 and 2. Well, where there's a null hypothesis, there is an alternative hypothesis. So for the alternative, if this is equals, the alternative is not equals. Now, as we're testing two of any measure, in this case it's two means, we're really not going to be able to statistically test to see if this equals that, because what we want to do is to put this on the normal curve. We're going to have, let's see, this is a two-tailed test. We're going to have two rejection areas. We want a number, and we want to see if that number lands us in the rejection region or in the fail to reject region. So instead of having these two measures compared together, we're actually going to take that just for the sake of the mathematics. You can leave your hypotheses as is, but we're going to take this equation and we're just going to move one of the means to the other side. So we're going to turn that into a difference. Mu sub b minus mu sub g equals 0. Some books call this a test of the difference. So now we can come up with either that difference equals 0, or for the alternative, it's not equal to 0. Well, we are expecting some kind of a difference in their heights, right? So we do expect it to not be 0. We just want to know if that difference, and we're going to put that difference over here somewhere, wherever it lands, if that difference is significant, or if that difference is just because of chance, if it's not significant. So mathematically, that's how we're going to turn this problem that involves two means into something with a single measure. Okay, so step number 2. Step number 2 is that critical value. We've already done a lot of the prep work here. We showed that it is two tails. So two tails, alpha is 0.05. I just need table F from my figures and formula card, or table F from the back of the book. So here we are, table F. I have a two-tail test, just like I'd look it up for any test. So two-tail test, 0.05 puts me here. I don't need degrees of freedom because I have large sample sizes, so I go all the way to the bottom, and I end up with a critical z-score of 1.96. It's a two-tailed test, so I know to put in the plus or minus 1.96. So our critical value, same step as we've had before, plus or minus 1.96. So to be significant, I have to be either to the left of negative 1.96 or to the right of positive 1.96. Okay, step number 3 is to figure out our test value. And our test value is the z-score for the sample. And in this case, not just mean, but for the sample means. Well, to get through the test value, we are going to use the formula that we'll see in the figures and formula card. Remember, you'll have this with you, so you want to be familiar with what's here so that you're able to use it. We're in Chapter 9. And look, it calls it testing the difference, and that's exactly what we're doing. We know that they're going to be different. We want to see if that difference is significant or not. Here's our formula. Notice how it is a z-score formula. I'm taking the sample mean difference minus the hypothesized mean difference. So this would be x bar minus mu, but in this case I'm doing differences, divided by, and I've got this altered standard deviation. So the standard deviation is adjusted for the sample size. So I'm going to go ahead and use that to figure out what the test value is. And it's right off of the figures and formula card, and you'll also see that, of course, in Chapter 9. So here's our formula. I'm going to write it down in general so I can break it down for you. X bar 1 minus x bar 2. In parentheses, this is the sample difference minus the hypothesized difference, mu1 minus mu2, all divided by this altered standard deviation. And it's altered for the sample sizes. So standard deviation of one of them squared divided by n1 plus the second one squared divided by n2. Do you remember what a standard deviation squared is? A standard deviation squared is a variance. And in this particular problem, they gave us the variances. This is the formula, and I want to go ahead and show you what we have up above. So as I look up above, remember that null hypothesis? That null hypothesis means that the difference equals 0. So when I look at this formula, this always is 0. To get to x bar 1 and x bar 2, that's going to be the sample mean for the boys and for the girls. So I replace those values with these. So that's going to be 123.5 minus 126.2. And for my denominator, let me go ahead and just rewrite this whole thing now. This will always be 0, so that will always go away. So in your numerator, you want 123.5. Notice I'm using parentheses, minus 126.2. That's because I want to divide that entire difference by the square root of, and I'm going to put parentheses here. This is the variance. And in this particular problem, I was given the variance. So I'm going to go ahead and pick up that variance. So it's the sample variance, so it's actually S1 squared, but they have sigma, and we'll use that for sigma, and S2 squared. So I'm going to use 98. I'm not squaring it because the variance is already squared. So 98 divided by N1, where was that sample size? 60, plus the second variance, which was 120, divided by, that one was 50. Close parentheses. So I'm going to go ahead and just type that into my calculator exactly like you see it. So I'm not going to change anything as I'm typing this into my calculator. So I've got parentheses 123.5 minus 126.2 divided by square root of parentheses 98 divided by 60 plus 120 divided by 50. Close parentheses. And there's my critical z-score, I'll call that negative 1.34. So let me pull this off. So my test value is about negative 1.34. Okay, so remember that normal curve that we had put up here before. I am looking for a significant difference. So if I am in between those critical values of negative 1.96 for a z and positive 1.96 for a z, I'm going to fail to reject the null, which means no difference, no significant difference. I'm just being lazy. If I am to the left of negative 1.96 or to the right of negative 1.96 in one of those tails, that means I am going to reject the null hypothesis And that means that we have found a significant difference. Same thing over here. I'm just going to write reject. I'm going to reject the null hypothesis. Well, what we found was not significant. Remember, zero's in the middle. We found negative 1.34. So we have fallen into the not significant region. We found that they're different. These two average heights are different for boys and girls, but not significantly so, especially based on the variance that we found within those samples. So our conclusion then, we're on number 4, our conclusion or our decision is to say, let's see, we didn't find a significant difference, so we fail to reject. Fail to reject the null hypothesis. Remember, number 4 is always either, it's your decision, fail to reject the null or reject the null. But number 5, what does that mean? What that means is that there is not a significant difference. Not a significant difference in the mean heights of 9-year-old boys and girls. Notice how I am not girls. Notice how I am writing a sentence and I am explaining what fail to reject means. This is a really important part of what we do in these. I want to make sure that you understand what you're doing, not just going through the motions. What does it mean to fail to reject? Well, we were trying to find something that was significantly different than 0. And to be there, we had to be at negative 1.96 or below, or 1.96 and above. We didn't get there. So we're finding a difference, but it's not significant. So I just concluded there's not a significant difference in the mean heights of 9-year-old boys and girls. There's a second way that we can do this, and I think you're really going to like the second way. I don't want to hold out on you because I think it's important to be able to do the test by hand, but also important to be able to do the test with the calculator. So the calculator does a really nice job of hypothesis testing. Again, this makes it all that much more important that you're able to explain in that summary what you're doing. So I'm going to go ahead and use this data again, see if I can find a spot here where you can see what's going on in my calculator. I'll try right there. I'm going to go to the stat menu, over to tests, and I'm going to go down to, this is a 2-sample test of the means. Well, the proportion tests are labeled nicely, the mean tests aren't. So I know it's going to be one of those. It's a z-test because I have large sample sizes, so I pick the 2-sample z-test, which is number 3 on my calculator. I hit enter, and it says, are you going to give me data or stats? Right now, mine's set up for data, so it's asking me where I put the data. I don't have the heights of all those kids. I just have the calculated mean and variance. So I want to move over to stats. So I'm going to hit stats and enter. Now it's going to start asking me for what I was looking for. But look what it's asking for. It's asking for a standard deviation. I was given a variance. So for right here, instead of typing in 98 for the standard deviation, 98 is my variance. So I need the square root of that. I need the square root of 98. Enter. You have to be really careful. If it gives you a variance, your calculator's asking for a standard deviation. So I need to take the square root. Same story here. So I want the square root of that second variance, which was 120. And now it wants to know what the mean was for the first sample. That was 60. See how it's nice to label those, sample 1 and sample 2? And that sample size, oops, I'm backwards. The sample mean was 123.5. And the sample size was 60. Now on to sample number 2, the girls. The mean was 126.2, and the sample size was 50. And now it's asking you for that alternative hypothesis. Ours was not equal. But remember, if you wanted another one, you could arrow over and hit enter, but I do want that one. So I'm going to arrow down one more time, and I'm ready to calculate. And take a look at what it gives me. It gives me in about, what, a second, 2 seconds? It gives me that z-score. That's exactly the test value that we computed. Where was that? So we did a good job. So here's our test value, negative 1.34. That's exactly what we got. It gives us this nice bonus. It gives us the p-value. And with that p-value of 0.1789, 0.1788, we can see that this is bigger than the alpha, bigger than 0.05, which means that my area, the p-value area, does not fit in the rejection region. It spills into the fail to reject region. So I could also conclude fail to reject based on my big p-value. And then it just confirms with you what you gave it. So it just says you gave me these 2 sample means, and those are the sample sizes you gave me. Isn't that great, though? So you should still be able to go through and use what you've got here. You still need table F to come up with those 1.96, but you can still step through that 5-step procedure using your calculator. And this way, using either the traditional method, which is what we used, or you can use your 0.1788 for the p-value for the same conclusion. Okay, so let's do another example. Here's my second example. This one is with proportions. Let me put it up here. So in the second example, it says in a sample of 200 men, 130 said that they used seatbelts. In a sample of 300 women, 63 said they used seatbelts. Test the claim that men are more safety conscious, meaning that more men wear seatbelts, than women at alpha equal 0.01. Use the p-value method. So as we go through this one, let me go ahead and set up some of our values. So we have the men, and I'm going to call that sample number 1. And we have women, and I'm going to call that sample number 2. And we are given our sample size, so n. So n is 200. The 130, that's my x. So x. And you know what I'm going to do? So I can label these nicely. I'm going to say n1 equals 200. x1 is 130, so it's 130 out of 200. Over here, n2 is 300. And of the women, so x2, we had 63. Test the claim that men are more safety conscious than women using alpha equal 0.01. I'm going to follow this up with the calculation, and what I really need here is the sample proportion, and that sample proportion is p hat. But I have one for each of the 2 samples. So p hat sub 1 is going to be the 130 out of 200, so x1 over n1. So 130 over 200, what is that? 130 divided by 200 is 0.65. So P1 hat is 0.65. And then for P2 hat, same story. So 63 over 300. So P2 hat is equal to 63 over 300. 300 is 0.21. Okay, so now we have a handle on all of our sample data. Let's go ahead and move through the 5-step. With the p-value, I do a 4-step process. So we'll move through the 4-step process. The claim, test the claim that men are more safety conscious, which means I'm expecting their proportion to be significantly higher than the women's proportion. Let's put that down into a hypothesis. So null hypothesis, alternative hypothesis. More safety conscious means I'm expecting their proportion to be more than the women's proportion. Okay, before I write it down, should this go in the null hypothesis or the alternative hypothesis? I'm using a strictly more than symbol, so if you said alternative, you're correct. I don't use the sample, though. For the hypothesis, I always use my parameters, so I'm not going to have the hats on it. So P1, so in general for all men, would be greater than P2, that proportion. Not just our sample, but for all men is what we're hypothesizing. And then that makes our alternative P1 less than or equal to P2. Okay, so same story. Mathematically, we're really checking a difference. So P1 minus P2 is less than or equal to 0 if I move that to the other side. P1 minus P2 is greater than 0, but you don't need to write those down. This is fine. Just know that mathematically that's what we're looking at. Remember, we always assume the null hypothesis, innocent until proven guilty. So we assume the null hypothesis, which means for this case that we're assuming that it's either less than or equal to. So we're assuming that the proportions are the same. P1 and P2 are the same. So we have one additional calculation for this problem, and that's to do the overall proportion. So for everybody all together in these two samples, I want the overall proportion. We call this P bar. So P bar is everybody, okay? Everybody that wore a seatbelt that we talked to, doesn't matter if you're a man or a woman, that would be 130 of the men and 63 of the women. So everybody that wore a seatbelt, 130 plus 63 divided by everybody in the sample. Well, everybody in the sample, there were 500 total between those samples. So what is that? 193 over 500. So I take 193 divided by 500, and I get 0.386. So I've got this P bar, this overall proportion, assuming that doesn't matter if you're a man or a woman, they're the same. And I also need Q bar. So Q bar is 1 minus P bar, not unlike our binomial stuff from the past. So 1 minus 0.386, which would be 0.614. So there is P bar and Q bar. Now, if you're getting overwhelmed with these formulas so far, don't, because you're going to have all of the formulas, most of them anyway, on your formula card. So if I take a look here at what we have for proportions, I'm in Chapter 9. It's hard to read because this is laminated, but what we have here is I'll zoom in. I'm on the Figures and Formulas document. Mine's a laminated card. I'm going to be looking at the difference between the sample proportions minus the difference between the hypothesized proportion. That's going to be 0 every time. This guy just goes away. They just have it there, I don't know, just to confuse us, I guess. That's always going to be 0. And then in my denominator, I've got this, again, an altered standard deviation. So there's those bar, P bar and Q bar, and then I'm adjusting it for the sample size. So as I put all this together, I'm ready to compute my test value. But I'm going to, what am I doing? A p-value? P-value method. You know what? Let's do this because I want to show this to you on the calculator. Let's do the traditional method by hand, and then I'll show you the p-value method with the calculator, and you can see how you can combine the two. So let's go ahead and do the traditional the traditional method first. Okay, so we'll continue. Let me zoom in just a little bit more. So let's continue with the traditional value or method. Continue with the traditional method, which means we want a z-score. Traditional method. Okay, that means that what we need is the critical value. Critical value. Where's my hypotheses? My hypotheses are less than or equal to and greater than. That gives us a one-tail test to the right. So we have one tail and alpha was 0.01. So I'm going to go and flip over to table F here. You guys might have some of these memorized. I just want to remind you where they are. 0.01 one-tail test. One tail, 0.01. Here I am, all the way at the bottom for my big sample sizes. 2.326. A lot of books call that 2.33. I'll use 2.326. So my critical value is positive, because I'm on the right, 2.326, or 2.33 if you want to round. Okay, there's my critical value. So that's right here, 2.33. 0 still in the middle. So in order to reject, I need to be bigger than that. Fail to reject, I would be smaller than 2.33. Step number 3, test value. For the test value, I'm going to use the formula. I'm just going to copy this right off of my formula card. I don't have this memorized. I've got way too many other things in my brain to have this memorized. I'm going to copy this right off of the formula card. hat minus P1 minus P2 divided by the square root of P bar Q bar, look that up, P bar Q bar, parentheses 1 over N1 plus 1 over N2. Okay. We're hypothesizing in our null that they're the same. So this always goes to 0. So when you're computing this, you're really just doing that piece, exactly like the last example. And I'm going to go ahead and put some values in. So z is equal to, let's see, we already computed P1 hat, and that was 0.65, so parentheses 0.65, just looking at my work above. P2 hat for the women was 0.21, divided by square root, parentheses, P bar, where's P bar? 0.386, that was the overall proportion, times Q bar, which was 1 minus that, 0.614, times, in parentheses, so parentheses, 1 over, I had 200 in that first sample, plus 1 over 300, close this parenthesis, close that parenthesis. Okay, phew. It is helpful if you write it down. So I know it's kind of a pain to write everything down. I can't tell you how many mistakes I find in this particular calculation just because someone didn't keep track of their parentheses. So writing it down is a great way to go. So I'm going to go ahead and type this in. I am going to show you my keystroke so that you can see exactly how to get from here to the answer. Let me clear that. So parenthesis 0.65 minus 0.21, parenthesis, there's my numerator, divided by second square root. I am going to use parentheses, 0.386 times 0.614, parentheses that open. Now I'm going to use 1 divided by 200 plus 1 divided by 300. I'm going to close the first set of parentheses, close the second set of parentheses, and then I can hit enter. So there we go. So there is my test value. So my test value is huge. Remember, these are z-scores. A z-score of 3 is very significant. We had a z-score of 9.9 in this one. Huge. So we've got a z-score of 9.9. So I'll bet you know what that conclusion is. I am way, way, way far away from that critical value. Step number 4, this is my decision. Okay, 2.33. I ended up, let me go out a little further. I ended up with, way over here somewhere, 9.9. So I am well into that tail on the right, which is my rejection region. So this is my rejection region, significantly far away from 0. So my conclusion, or I'm sorry, my decision is to reject the null hypothesis. That's all you need. Step number 5 is where you need to do some thinking. I'm going to reread that problem to you. Test the claim that men are more safety conscious than women. So we're claiming that men are significantly more, or they more frequently wear seatbelts than women. Is that true? Yeah, we found a huge difference. So yes, significantly many more men. I'm just going to say significantly more men wear seatbelts than women. Notice how I use that significantly word again. It's so important because you're not just showing there's a difference. I expect there to be a difference. This was a sample. And we're really showing a significant difference than women. Okay, so I promised that we would do it using the calculator. So I'm going to go ahead and do a p-value method using the calculator. But I want you to think back through what we just did and how you can use the calculator for that as well. So what I want to do this time is put it up here. I want to do another test, get it in one of the lights. So I'm going to do another test. I'm going to go stat, over to tests, and then I'm looking for a 2-sample proportion test. There it is, number 6. And it's asking for X1 and N1. Those were given to me, right? So here they are. I'll at least show it to you for the men. X1, that was 100. Oh, look, I already put everything in here. So that's 130. N1 is 200. X2 is 63. and N2 is 300. And it says, do you want not equals, less than, or greater than? What did we have? Here's my hypothesis. We had greater than. So I'm going to arrow over to greater than, and then hit calculate. Okay, I always take a little sigh of relief at this point because I know that I calculated my z-score using the traditional method correctly. There it is, 9.9. We're using a p-value method, though. And what we ended up with for the p-value is this teeny, 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 tiny guy. Let me step through the p-value method so that you can see what I'm looking for. I do it just a little differently than your book in terms of the steps. For the p-value method, step number 1, still the hypotheses, so no change there. Where were they? P1, no hats or anything, less than or equal to P2. Alternative, P1 greater than P2. Step number 2 is the p-value. I love using the calculator for p-value methods because it just gives it to me. The p-value is 2.1 times 10 to the negative 23. Do you know how little that is? That would be 0.1, 2, 3, 4, 5, 6, 22 of those zeros before we hit that 2 and then a 1. Tiny area cut off by the difference. And if you want to say sample difference, test difference, whatever. Tiny, teeny, tiny area. Well, I really wanted that area to fit into the area of the significant region, which was 0.01. Remember, we're not talking cutoffs now, we're talking areas. So the area of the significance region, area equals 0.01. So that's the size of this area here. The area that I found was teeny tiny. It's like a little teeny tiny speck down here. And I always fill in those p-value areas from the tail, and it fits well within that tail. So 0.01 is bigger than my p-value, which is this guy, which means that the p-value stays in the rejection region, so we reject. So step number 3 is to reject the null hypothesis. We already knew that, but I needed to verify that using my p-value. And then step number 4, and I already wrote all that out. I'm just going to say same as 5 above. We did show that there is a significant difference between the proportion of men that wear seatbelts and the proportion of women. Okay, so there is the 2 sample tests, and we've seen an example of each one. Also in this chapter, there are 2 sample tests of the means for small samples, and we're not going to do those. So we're just going to be looking at the test of the means for large samples and then the test of the proportions in this chapter.